Chapter 10, Section 3, Taylor's Theorem. On page 504, exercise 2, there's a function in the textbook. It does not have a name. I'm going to give the function a name, f of x. What's given is the cosine of pi over 2 times x. And the directions are to find the Taylor polynomial of order 4. The symbol for that is P for polynomial, subscript 4. Find the Taylor polynomial of order 4 for the function at x equals 0. The second part of the directions, we're not going to worry about that today. We're just going to do this part. So we find up to the fourth derivative of this function. The derivative of cosine pi over 2 times x is the sine of pi over 2 times x times pi over 2. Actually, the derivative of cosine is negative sine. This pi over 2 is here because of the chain rule. Second derivative, the derivative of sine of something is the cosine of the same thing times the derivative of this thing in here, which is pi over 2, but there's already a negative pi over 2 there, so we end up with negative pi squared over 4. Using the pi over 2 already there and the chain rule. The third derivative, the derivative of cosine is negative sine. There's already a negative there, so we'll have negative negative, ending up with positive sine of whatever's here, pi x over 2, times pi over 2 because of the chain rule. So that pi over 2 that I just mentioned gets multiplied to the number that's already there. So pi cubed over 8. The negative is gone because the derivative of cosine is negative sine. The fourth derivative, the 4 looks like an exponent, but putting parentheses around it indicates the fourth derivative, not to the fourth power. The derivative of the sine of something is the cosine of the same thing, pi x over 2, times the derivative of pi x over 2, which is pi over 2. Multiplying pi over 2 by the number that's already there, we have pi to the 4th over 16. So now we evaluate the function and all of these derivatives at 0. So we need the function evaluated at 0, f prime evaluated at 0, f double prime evaluated at 0, the third derivative evaluated at 0, and the fourth derivative evaluated at 0. Well, x is 0, pi times 0 over 2 is 0, and the cosine of 0 is 1. X is 0, pi times 0 is 0, 0 divided by 2 is 0, the sine of 0 is 0, 0 times whatever is 0. So that's coming from there. Cosine of 0 is 1. 1 times negative pi squared over 4 is negative pi squared over 4. The sine of 0 is 0, so the third derivative at 0 is 0. And the fourth derivative, since the cosine of 0 is 1, 1 times pi to the 4th over 16 is pi to the 4th over 16. So here's the what we call a Taylor series, which in this problem we could also call a Maclaurin series. And the reason we can call it Maclaurin is because it's at x equals 0. If it were at x equals some other number, we would just call it a Taylor series. So any function, this is a review, a reminder, any function is the function evaluated at 0, in this case, because Maclaurin, plus the derivative evaluated at 0 times x minus 0 to the first power over 1 factorial, plus the second derivative evaluated at 0 times x to the second over 2 factorial, plus the third derivative evaluated at 0 times x to the third over 3 factorial, plus the fourth derivative evaluated at 0 times x to the fourth over 4 factorial, etc. This is, in general, the Taylor series for any function. If I don't say etc. here, these 3 dots at the end, well, then I would, instead of using equals here, I would use approximately equals. And that's what we're going to do here, because we are not getting a Taylor series, we're getting a Taylor P for polynomial. The function in this exercise is cosine pi x over 2. We're going to say that can be approximated with a polynomial, 4th order, function of x, a polynomial function of x, which we I just fill into here. So for the function in question, f of 0, all these numbers that we figured out here are going to get plugged in here. F of 0 was 1. We have a plus. F prime of 0 was 0, so this will say 0 times x, plus f double prime of 0, that was negative pi squared over 4. Don't forget the over 2 factorial with x squared next to that, plus third derivative at 0 was 0, so this will be 0 over 3 factorial, which is 0, times x cubed, plus the fourth derivative at 0, that was pi to the fourth over 16. Don't forget over 4 factorial with x to the fourth next to it. So I'm stopping here. This is not a series. This is not a series. This is a Taylor polynomial. Series would go forever. Simplify. The cosine of pi x over 2 is approximately this polynomial. 1 minus, well, this, I said minus because this term disappears, and here's a plus a negative. And this number, pi squared over 4 over 2 factorial, can be simplified to pi squared over 8. X squared is next to that. Then there's a 0 term. 0 times x cubed is 0. And then there's this last term here, pi to the fourth over 16 over 4 factorial is pi to the fourth over 384. X to the fourth. That's the answer to exercise 2. This is a Taylor polynomial right here of order 4. In other words, it has a fourth degree, 4th power of x in it. And this can be used to approximate, this polynomial can be used to approximate this function as long as x is near 0. For x near 0. So I wanted to mention another way to do this problem that's really important. So we're going to redo exercise 2 differently. You have a list of Taylor series for commonly used functions. One of them is this. Cosine x equals sigma n equals 0 to infinity, negative 1 to the n times x to the 2n over 2n factorial. And that's can be expanded. That can be expanded by replacing n with 0, then 1, then 2, then 3, etc. So when we replace n with 1, all this comes out to be 1. 2 times 0 is 0, and 0 factorial is actually 1. When n is replaced with 1, all this comes out to be negative x squared over 2 factorial. Replace x with 2. All this comes out to be positive x to the 4th over 4 factorial, etc. So you have a handout that has this on there. If you could memorize this, it's recommended that you memorize the Taylor series for commonly used functions. Then a problem like exercise 2 on page 504 can be found by replacing every x with pi x over 2. Replace every x with pi x over 2. So I'm just doing copying right now, but everywhere I see x, I'm replacing it with pi x over 2. Right here, instead of writing x to the n, I'm going to put pi x over 2 to the 2n. Copy everything, copy anything that's not an x, like so. Expand it out, same thing over here. There's a 1, there's a minus. Right here, do not write x squared, write pi x over 2 squared. So these things right here are the same, except x is gone and pi x over 2 is in its place. Same here. X to the 4th, get rid of the x. Instead of writing x to the 4th, write pi x over 2 to the 4th, etc. So to answer the exercise, which did not ask for a series, this is actually a Taylor series, because we're going right here, infinity, dot, dot, dot. To answer the question, find the Taylor polynomial of order 4. The Taylor polynomial of order 4. It's just these 3 terms simplified. So you should verify that these 3 terms, when simplified, are the same thing we got a few minutes ago, which was 1 minus pi squared over 8 times x squared plus pi to the 4th over 384 times x to the 4th. The end. That's the no dot dot dot, because this is not a series, it's a polynomial. 4th order. So just pointing out that this is quicker. I know these messy things might take a little bit of time to simplify that to just that. But this is quicker and more efficient than finding all these derivatives, plugging 0 into all of the derivatives, and then plugging all of those results into this. Either way, it's the same final result. So we're going to now do number 8 on page 504. We're looking for the Maclaurin series for the function cosine squared x. The hard way to do it is to, like we just did in the last one, the first time we did it, we find all the derivatives, then evaluate all of the derivatives at 0. And I'm saying 0 because of the word Maclaurin is in the directions. And then after finding the derivatives and all the derivatives evaluated at 0, plug the results we get into this. This is Taylor series or Maclaurin series for any function. Well, instead of doing that the hard way, we're going to take advantage of the fact that cos squared x is exactly the same as 1/2 plus 1/2 cosine 2x. That's a trig identity that's actually given as a hint in the question, in the directions. So I know that the cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial dot dot dot. The nth term, the general term, is negative 1 to the nth. That is what makes the signs alternate: positive, negative, positive, negative. X to the 2n, because the first exponent is x to the 0. 2 times 0 is 0. This is 2 times 1, this is 2 times 2. That's why the exponent is 2n. Of course, it's over 2n factorial, because these numbers on the bottom are always matching those exponents. So what we're going to do, instead of finding all those derivatives, we're going to just replace every x here with 2x. Cosine. Get rid of the x, put a 2x there. Copy, copy, copy. Instead of x squared, write 2x squared. Go back to copying, copying. X to the 4th, it's going to be not that, it's going to be 2x to the 4th. Copy, copy. X to the 6th becomes 2x to the 6th. In the general form, the general term is negative 1 to the n. Instead of x to the 2n, it's going to be the quantity 2x to the 2n. Just copying 2n factorial. Just simply replacing all the x's in the memorized Taylor series for cosine x, replacing all the x's in that series, memorized, replacing all the x's with 2x. So now, go back up here, and we're almost done here. Cosine squared x equals 1/2 plus 1/2 times this big thing right here. So it's 1/2 times all this. 1 minus this is 4x squared over 2 factorial plus this is 16x to the 4th over 4 factorial minus this is 64, I think, x to the 6th over 6 factorial, etc. And this nth term here, we'll just leave it like that. Negative 1 squared, negative 1 to the n, sorry, that's supposed to be an n, times 2x in parentheses to the 2n over 2n in parentheses factorial. And if you wanted to distribute this 1/2, well, maybe we should do that a little bit. Cos squared x equals 1/2 plus 1/2 times 1. So just distributing this 1/2 out here. That next term is going to be positive times negative, so it's going to be negative 4x squared over 2 times 2 factorial on the bottom there. The next term is a positive times a positive, so that's positive 16x to the 4th over 2 times 4 factorial. Etc. I want to get to the general term. This is the hard part. The general term, this mess times 1/2, is going to be negative 1 to the n times 2 to the 2n times x to the 2n. I'm just raising this 2x to the 2n over 2n in parentheses factorial with a 2 also because this denominator and this denominator have to be multiplied, etc. Well, here we have like terms, 1/2 plus 1/2, so we can just say that's 1 minus this fraction reduces to just x squared because 2 times 2 factorial is 4. 4's cancel. Plus this fraction, 2 times 4 factorial is on the bottom, 16 is on the top. So that'll reduce to x to the 4th over 3, etc. So here's the nth term. It's negative 1 to the n. So here I see a 2 to the 2n, and down here this 2 to the 1st. So that can be written as 2 raised to the 2n minus 1, because the rule for dividing with like bases is keep the base, 2, and subtract the exponents. And there's also an x to the 2n that's still there in the numerator. And the denominator now just has the 2n in parentheses factorial, because we took care of that 2 by doing the division. And we are done with that exercise. So I'll end this video here, and we'll say more about this section, Taylor's theorem, in a separate video.